Hello and welcome, everyone. Welcome to the Foundations of Physics seminar series. We're thrilled to have Chip Sebens from Caltech, who'll be talking about potential energy in classical and quantum electrodynamics. You should be able to see Chip's slides now. Just a couple of notes about this seminar and the seminar series more broadly. So as hopefully everybody here saw from the email, the seminar is going to be every other Tuesday. We're going to continue on a schedule of starting at 1 p.m. Eastern time. Each talk will be 1 hour. There'll be a 5-minute break, and then we'll use the rest of the following hour for Q&A and discussion. We'll have a lot of time for questions and discussion. So if you have a lengthier question during our speaker's talk, I'll ask that you hold on to it until the question and answer period. If you have a quick clarification question, please do not unmute yourself. Just put the question in the chat. I will be monitoring the chat. And if it looks like it's a question that we should get the speaker's attention for, I'll notify the speaker. I think that's it. So I'll ask if everyone can please stay muted during the talk. We are recording this. And then obviously when we get to the question answer period, feel free to unmute. During the talk, if you have a quick question and I call on you, I guess at that time you can unmute. That's it. So welcome everybody. And I think unless there's anything else, Chip, are you ready to get started?
Yeah, I'm ready.
All right, so take it away.
Okay, thank you so much, Jacob. I'm very excited to be speaking to this group. I wanted to start before jumping into the questions that will be the focus of today's talk with just a little bit of background on where I'm coming from, what some of my motivations are, and what kind of approach I'm taking to these issues. So I'm a philosopher of physics, and philosophers of physics are interested in many different kinds of questions, but I'm foremost interested in questions about laws of ontology. So give me a theory in physics, and I want to say, what is that theory actually telling me about reality? What kind of picture is it painting of the world? What is out there? How is that stuff described mathematically? What laws govern the behavior of that stuff? These are the kind of questions that I'm interested in. Quantum mechanics is a theory where it's famously hard to say what it's really about, what's actually going on. Classical field theories are generally taken to be more straightforward, but I think there are interesting questions there as well. Quantum field theory, I think, is quite hard to get clear on the laws and ontology. So this is kind of what drives me. For an introduction to this kind of approach to the philosophy of physics, I like Tim Maudlin's Ontological Clarity via Canonical Presentation, Electromagnetism and the Aharonov-Bohm Effect. So let me just plug that paper. He goes through different ideas about what you might posit as the ontology and laws for classical electromagnetism. Okay, so I'm interested in these questions about laws and ontology. I'm also curious about the relationships between different theories. I take a kind of comparative approach often. So I'm curious what is retained and what is jettisoned in the move from one theory to another. And I tend to think new theories aren't as radically different from old theories as they're often presented as. So I think that new physics often, or more advanced or more fundamental physics often retains many aspects of old physics. And it's interesting to try to find those continuities to see what is retained and what has changed and to be clear about that. And today we'll focus particularly on the relationship between classical field theories and quantum field theories. So what aspects of classical field theory are retained in quantum field theory, looking at that border. Okay. When you look at quantum field theory and you try to get clear the laws and ontology, you try to figure out what it's a theory of, it's hard. There are different ideas you might put forward. In my eyes, the main big dividing line is whether you think of quantum field theory as a theory of particles or fields fundamentally. Obviously, at some level, it's a theory of both particles and fields. But can we think of it as fundamentally a theory of particles, fundamentally a theory of fields? Ultimately, you'd be interested in articulating such a picture of quantum field theory for all the particles or all the fields for the entirety of the standard model. So you'd want to figure out, is this a theory of electrons, photons, up quarks, down quarks, all of these particles, here shown in fun, cute cartoon versions, or is it a theory of a bunch of fields, like the electromagnetic field? So we could ask it about the entirety of the standard model. That gets very hard. Today, we're going to focus on just quantum electrodynamics. So just 2 or 3 of those particles or just a couple fields. So we've been looking at the electron, the photon, and the antiparticle of the electron, the positron. So that will constrain our attention to that today. Okay. So on this divide between particles and fields, I think of quantum field theory as a theory of fields. Okay, so in particular, I take quantum field theory as a theory of fields in superpositions of different classical configurations, different classical states that field might be in. So just as ordinary non-relativistic quantum mechanics is often presented as a theory of particles and superpositions of different locations, I think of quantum field theory as a theory of fields and superpositions of different classical configurations. So for particles and superpositions of different configurations, you might describe them with a wave function. So the wave function would take in a particular set of locations for some point particles, and it would return an amplitude, a complex number. If we're instead having a theory of fields instead of particles, you can use a wave functional. What the wave functional does is takes in a possible classical state of the field, shown here as some scalar field phi, and returns a complex amplitude. It's called a wave functional because it's a function of a function. The field is already a function on space, and the wave functional takes in that function of space and returns an amplitude. So I think of the ontology of quantum field theory as involving these wave functionals. You might want to add more beyond the wave functionals, but at least you have these wave functionals. And then as far as the laws go, at least one of the laws for quantum field theory is going to be a Schrödinger equation giving the time evolution of wave functionals. So that's at least a broad picture of what I see as the laws and ontology of quantum field theory. I think this field approach to quantum field theory also comes with a picture of how you get to a quantum field theory. There are different ways to get to a quantum field theory, different ways to build it up or to say what it's about. But I think one helpful route to examine is this route of field quantization. So you start with a classical field theory, and then you quantize and you get a quantum field theory. So today we'll be talking about, moving from a classical field theory to a quantum field theory. Okay, so this is kind of a broad sense of how I look at quantum field theories, what I think they're theories of. I'm not going to give a detailed defense of this today. I'm sort of taking this as the approach I'm running with, and we're going to examine some questions with this broadly in the back of our minds. Elsewhere, I've recently written about the advantages of this field approach over a particle approach and the challenges that it faces. In this paper, The Fundamentality of Fields. It's to some degree sort of common sense for people to say that quantum field theory is a theory of fields. If you ask a lot of people, I think that's where they would lean. But this idea of spelling out the ontology in terms of wave functionals faces real problems. It's not so straightforward to say that this is how the theory should be formulated. So even though ultimately I'm a fan of the field approach, I think it faces real challenges that need to be overcome. So I think there's work to be done to develop this approach and to make it successful. So this is where I lean, but I don't think it's an easy question. I don't think it's an obvious answer. I think that's subtle, and I think there's work to be done. Okay, so that for background. Now let me get into the plan for today's talk. So for today's talk, I want to address two separate questions, and I'm talking about two separate papers. In a way, they're really two quite distinct questions that I'm focusing on, but there are some connections between them, and talking through the first question is going to lay the groundwork for discussing the second question. So in that way, it will be helpful to discuss them together today, but they are separate questions. Okay, so the first question is whether potential energy is part of fundamental physics. Does potential energy survive when you go to more advanced or more fundamental physics or not? So we can look at a series of theories. So today we're going to look at 4 different theories: classical electrostatics, classical electrodynamics, classical Maxwell-Dirac field theory, which is classical electrodynamics with a particular model of matter, modeling matter with the classical Dirac field, and then moving from there to quantum electrodynamics. So in classical electrostatics, I show the rabbit here, rabbit representing potential energy. So in classical electrostatics, it's common to speak of potential energy, and you might think, oh yeah, there's potential energy there in classical electrostatics. I put a question mark next to the rabbit because there are other ways to formulate or understand classical electrostatics where there's not potential energy. So maybe potential energy. With classical electrodynamics, I put the hat because it seems like potential energy has disappeared. If you look at a textbook on electrodynamics, it seems like you don't need potential energy anymore. It's not part of the theory anymore. So you get this disappearance, at least on the face of it, but a question mark again, because I don't think that's decisive. Then you get the rabbit for classical Maxwell-Dirac field theory representing potential energy. So potential energy reappears. Potential energy is part of this classical field theory, I'll argue, and then it persists into quantum electrodynamics. Okay, so that's the first part of the talk. That'll be the majority of the talk. And then a briefer part of the talk on the second question, why doesn't the electron repel itself? So if you take the classical Dirac field to represent matter, then the way you would represent an electron is as a spread out distribution of charge and energy. Well, if it's a spread out kind of thing, then you'd expect the different parts of the electron to repel one another. And that seems to be part of classical Maxwell-Dirac field theory, that you have this self-repulsion. But physically, it's not actually there. Electrons don't repel themselves in this Coulomb way. So somehow it should be removed as we go from Maxwell-Dirac field theory to quantum electrodynamics. So I want to discuss how I see that as happening. Okay, so that's the plan for the talk. If we're going to be asking whether various theories have potential energy, we need to figure out a bit about what potential energy is, what we're looking for. An old idea is that potential energy is to be contrasted with actual energy. There's real energy, there's energy that exists, and there's merely potential energy. It's not actual energy. That's not how people generally think of potential energy now. One reason why that picture is unattractive is that if potential energy is not real energy, it's not actual energy, then actual energy wouldn't generally be conserved. Often it's only potential energy plus whatever other kinds of energy you have that is conserved, not the other energies on their own. So we can move past that idea quickly. Another possible idea is that potential energy is to be contrasted with kinetic energy. You might try to classify all energy as either kinetic or potential. Then the distinguishing feature of potential energy would merely be that it is non-kinetic. I think this is awkward. It sort of doesn't really pick out anything special about potential energy that makes it potential energy. It's just non-kinetic. And it forces you to classify certain things as potential energy that you might be hesitant to, or you might wonder whether they really should be classified as potential energy. So for example, if you endow the electromagnetic field with a kind of field energy, well, that appears to be non-kinetic energy. So it seems like that would have to be classified as potential energy. Also, if you're thinking about relativistic particle mechanics, a point particle at rest might have energy mc squared. Do we want to say that's potential energy? Not obviously. So, okay, so let's move past that idea. What I think is a better idea, better way of picking out potential energy is to say that potential energy is extrinsic energy. It's not energy possessed by a thing in virtue of its own properties alone. It has to do with relations between that thing and something else. It has to do with its connection to something outside of itself or beyond itself. So for example, if you have a tennis ball in the air above the earth, as in this picture, you might say that the potential energy of the tennis ball depends on its distance from the ground or its distance from the center of the earth. So it has to do with its relation to the earth. And in that way, it's extrinsic. Or putting it a bit differently, maybe you say the potential energy of the ball depends on what's going on with the gravitational field where the ball is, the strength of the gravitational field at the ball's location. So there it's depending on something beyond the ball, but still located where the ball is. But either way, it would be extrinsic. Okay, so that's the broad picture I'll have of what potential energy is. If we think of potential energy as extrinsic energy, it makes it a difficult question how to discern between potential energy and what you might call interaction energy. So sometimes you see this language of interaction energy. As I think of it, potential energy is energy of one thing, energy possessed by one thing, but to some degree in virtue of its relation to other things, or in an extrinsic way that depends on its relation to other things. Whereas interaction energy would be possessed by two things together, sort of shared between them. And then you might ask, how would you ever know whether a certain kind of energy is potential energy or interaction energy? How can you make that cut? It's hard, maybe too subtle sometimes, or maybe there's no good reason. But later we'll see a case where I think you can give a good reason for classifying a certain kind of energy as potential energy instead of interaction energy. But we'll get there when we get there. Okay. So in electrostatics, we're starting at the beginning of that series of four theories that I want to go through. In electrostatics, we can ask first about point charges and how you might understand potential energy there. So here's a figure from my son's toddler level electromagnetism book showing a big charge and a little charge. And so you might ask, well, what's the potential energy of that little charge in the vicinity of that big charge with its strong electric field? Sometimes you might write that potential energy as Q phi, where Q is the amount of charge the little charge has, and phi is the value of the potential, depicted here as this kind of mountain, the value of the potential at the location of that charge. So plugging in a particular potential from a point source, that potential energy might be QQ over R. Yeah, you can write the potential energy as Q phi. But really that's the potential energy of the pair of charges. It's not right to say that that's the potential energy of the little charge in the vicinity of the big charge. That's the potential energy of the two in virtue of their arrangement of being a certain distance away from each other and having the charges they have. So if you're gonna locate that potential energy somewhere, it seems more reasonable to say, well, half of that potential energy is at the location of the little charge and half of it is at the location of the big charge. So then you'd say that the energy of the little charge is 1/2 Q phi, not Q phi. If we then move to charge distributions instead of point charges, the analogy of this 1/2 Q phi potential energy would be 1/2 rho Q phi, where rho Q is a density of charge and phi is the electric potential. So 1/2 rho Q phi gives you a density of potential energy in space. Our focus today will be on charge distributions. This is the only slide that mentions point charges. So after this, we go away from point charges and focus on charge distributions because I think that's the case that's relevant for understanding quantum field theory. Okay, so if we endow matter with this potential energy density of 1/2 rho phi, you will get conservation of energy in electrostatics, but we'll see shortly that that's not the only way to do so. There's a different option for getting conservation of energy in electrostatics. Okay, so here we kind of jumped right in. Let me back up and talk briefly about how I would put the laws and ontology of classical electrostatics. I mentioned earlier, this is how I think we should try to formulate physical theories and understand what they're about. So you have the ontology includes the electric field, which can be written as E, a vector field, or you could write it as a scalar potential phi, and then E is minus del phi. So you could use either phi or E to represent your electric field. Then you have some kind of charged matter. Classical electrostatics on its own doesn't tell you everything about that charged matter, but you'd have some charged matter with charge density rho, superscript q here, and a velocity field v superscript q. Okay. That charged matter acts as a source for the electric field by Gauss's law. So del dot E is proportional to rho. The electric field is divergenceless. This would be two of your laws. They look like two of Maxwell's equations, but for electrostatics. And then you have a force law saying how the electric field exerts forces on matter. For point charges, it would be F equals QE, but for charge distribution, you have a little f for a force density, you have rho for a charge density, and then the electric field E. Okay, so these would be laws for electrostatics. Just given these laws, nothing confines this to be a theory of statics. This could be a theory of dynamics, a theory that tells you how charges evolve and interact through Coulomb interactions, through electric attraction and repulsion. So we have a theory of dynamics here, even though I'm giving it the title classical electrostatics. It's a theory of dynamics. It's not a perfectly accurate theory of dynamics because it misses magnetic effects, but it's a theory of dynamics that we can talk about. Let me just mention as an aside that I'm using Gaussian CGS units in these slides. And so some of these equations might have different prefactors than you're used to, but hopefully not too hard to follow. Okay, good. So how do we write down equations for conservation of energy in classical electrostatics? Well, here are two options for how you might write down an equation for conservation of energy. Let's focus on the first equation first. Let's go to the red text. So what we have here, F dot V, gives you a rate at which energy is transferred to matter by electric forces per unit volume. So F is the force density, force per volume. V is distance over time. So you sort of have a force times distance on the top. You have a per volume and you have per time. So you can think of this as rate at which energy is transferred per volume per time. We can integrate it over all of space to get a rate at which energy of matter is changing as a result of electric forces. So then to balance that rate at which the energy of matter is changing, we need a rate at which some other kind of energy is changing. One option is to say that there's a rate at which the energy of the electric field changes. So we can endow the electric field with an energy density of E squared over 8 pi. If we integrate that energy density over all of space, we get the total energy of the electric field. If we take the time derivative, as is done here, we get a rate at which the energy of the electric field changes. Then the equation for conservation of energy would say when you add up the rate at which the energy of matter changes and the energy of the electric field changes, there's no change in energy overall. Overall energy is conserved. So that's one option for global conservation of energy in electrostatics. But that used a different energy density than the one we saw before. Before we had that potential energy density. This doesn't have a potential energy density. It has an energy density of the electric field, E squared over 8 pi. So the second option here uses the potential energy density from the couple slides ago. So for the second option, we still have exactly the same first piece, the integral of f dot v over all of space. But for the second piece, we use a different density of energy. We use 1/2 rho phi. So 1/2 rho phi then would naturally be interpreted as a potential energy density of matter. That's going to give you a different distribution of where the electric energy is in space. I'll show you shortly an example of that. It puts the energy in a different place and gives you a different idea of what kind of energy it is, not energy of the electric field, but potential energy density. That potential energy density can be written a different way. If you want to get rid of the phi, you can write it purely in terms of the charge distribution. So here I have 1/2 the integral of rho rho over x minus x prime. So what you're doing there is you're kind of summing up the QQ over R potential energy of each pair of charges for each combination of little bits of the charge distribution. So that will give you the same density over space. It's going to be the same distribution of charge, but a different way of writing it. Sorry, same distribution of energy, but a different way of writing it. You might question whether this really should be interpreted as a potential energy density. It could alternatively be interpreted as an interaction energy density. Maybe we should think of this as shared between matter and field. It's not potential energy of matter, it's interaction energy of matter and field. That would be a different way of talking about it, at least. Or maybe you think that this shouldn't be regarded as as a property of matter at all. Maybe it should just be a field energy density. Maybe you should regard it as a field energy density. In particular, if you use Gauss's law, you can replace the rho, which seemed to be describing the distribution of charge for matter, with the divergence of the electric field. So you can write this density purely in terms of field variables as del dot E times phi over 8 pi. So you might think that this is just an alternative energy density for the electric field that puts the energy in different places. Okay, so I mentioned a couple times there that the location of energy is different for those different options. So if we use the 1/2 rho phi option, where it looks like a potential energy density, then for a uniform sphere of charge, where the charge is distributed uniformly throughout the sphere, maybe you have positive charge, not just on the surface of the sphere, but on the inside as well. For that kind of case, the 1/2 rho phi option would say that there's potential energy spread throughout the sphere, a little more in the middle, a little less near the edges, but it exists all throughout the sphere and then nowhere outside the sphere. If the sphere has hard boundaries, then where there's no charge, there is no potential energy. Alternatively, if we use the E squared over 8 pi energy density, then the energy density is at a maximum on the surface of the sphere where the electric field is strongest. It fades as you get away from the sphere, but it's not zero outside the sphere. And it fades as you go into the center of the sphere where the electric field also goes to zero. So these two expressions give different ideas as to where the energy is, but when you integrate them over all of space, you get the same total energy, the same total electric energy. Okay, I can mention as an aside that you can make similar pictures for where the gravitational energy is of a planet in Newtonian gravity. So there too, you have the option of potential energy locating the gravitational energy within the planet, or field energy locating the energy in the gravitational field and having some of it exist beyond the bounds of the planet. Okay. So what should we think about these two expressions? Which one is the right one, or can we settle the right one? Here's what Griffith says about it in his authoritative and widely used textbook on electromagnetism. It says, where is the energy then? Is it stored in the field, as equation 2.45 seems to suggest, or is it stored in the charge, as equation 2.43 implies? Okay, I've rewritten versions of his equations in the notation used here. So is it this integral of e squared over 8 pi over all of space, or is it the integral of 1/2 rho phi over all space? At the present stage, this is simply an unanswerable question. I can tell you what the total energy is, and I can provide you with several different ways to compute it, but it is impertinent to worry about where the energy is located, at least within electrostatics. In the context of radiation theory, of full electrodynamics or electromagnetism, it is useful. And in general relativity, it is essential to regard the energy as stored in the field with a density e squared over 8 pi. But in electrostatics, one could just as well say it is stored in the charge with a density 1/2 rho v. The density is purely a matter of bookkeeping. The difference is purely a matter of bookkeeping. Okay, so this is interesting. He's saying, okay, maybe electrodynamics doesn't settle the matter. Electrodynamics is going to say it's useful to put it in the field, but not essential. I'm not quite sure what his reasoning is there. It's not fully explained. I think you have to endow the electromagnetic field with some energy in full electromagnetism to get conservation of energy. So it seems like some of that energy is going to have to be regarded as stored. There's going to have to be some energy regarded as stored in the field. But there is some indeterminacy about where you put the energy in electrodynamics. Okay, but in general relativities, it's essential to regard the energy as stored in the field. And the reason for that, I think, is that in general relativity, you're supposed to have a symmetric energy momentum tensor acting as in Einstein field equations. And the symmetric energy momentum tensor for the electromagnetic field has this e squared over 8 pi energy density in it, plus a b squared over 8 pi energy density for the magnetic field. Okay, good. Let me also mention here Mark Lang's excellent book, An Introduction to the Philosophy of Physics, Locality, Fields, Energy, and Mass. It also discusses this question of where the energy is located and questions about how the energy flows. It has a similar kind of lesson to this quote from Griffiths, which is, well, in electrostatics, you could use the potential energy density or the field energy density, but when you move to electromagnetism, it at least seems very compelling to regard the energy as in the electromagnetic field. So it seems like we get it resolved and figure out that it is field energy, not potential energy, when we go to electromagnetism. Okay, so here's why you can't just use potential energy in electrodynamics to get conservation of energy, why you're going to have to endow the field with at least some energy itself. So imagine this simple case. Imagine that you take this red charge, starts at rest, you accelerate it briefly, you quickly accelerate it, it moves at a constant velocity for a while, and then you decelerate it back to rest. So that's what you do. You exert force to accelerate it, you do work on it to accelerate it, and then it exerts force on you as you're catching it, as you're stopping it. So you, it does work. You get energy from the charge at the end. Okay. It doesn't seem like there's any way that the potential energy of the charge could have changed. It starts at rest and it ends at rest. Yet the amount of work that you put in is going to be more than the work that you get out at the end. So it takes more energy to accelerate the body than the energy you're going to get back from the deceleration. That's because of this radiation reaction effect. Okay, I'll get into more detail on radiation reaction later. But let me just say that if you attribute energy to the field, then we can say that energy has been carried away by the emitted electromagnetic waves. The reason why you don't get as much energy out at the end as you put in at the beginning is because this whole process has produced electromagnetic waves that are going off into space, and those are carrying away energy. Okay, but the only way we can say that these electromagnetic waves carry away energy is if we endow the electromagnetic field with energy. Okay, so moving to classical electrodynamics now from electrostatics, right? Being careful about the laws of ontology. We have the electric field, we have the magnetic field. They can be expressed in terms of the scalar potential phi and the vector potential A. We might want to group these together and say the ontology includes the electromagnetic field, E and B together. Maybe we want to represent that by E and B. Maybe we want to represent it by phi and A. Maybe we want to represent it by the Faraday tensor. There are different ideas. I'm not trying to be super careful about that here, but just somehow you have the electromagnetic field. You also have charged matter. As in electrostatics, there some charged matter with charge density rho and velocity field v. You have Maxwell's equations. I won't go through those. And then you have the Lorentz force law, giving the density of force exerted by the field on charged matter. That's often written for point charges, but here I've written it for a charge distribution. So the force density is equal to rho e plus 1 over c v cross b. Okay. So from those equations, we can derive an equation for conservation of energy in electromagnetism. This is the standard equation for conservation of energy in electromagnetism. The first part is just as before. The integral of f dot v over all of space gives the rate at which the energy of matter changes as the result of electromagnetic forces exerted on matter. The second part here with the green text, we now have an energy density of the electromagnetic field where part of it is just as before in electrostatics, e squared over 8 pi, and then we also have b squared over 8 pi for the magnetic field. Integrate that over all of space, you have the total energy of the electromagnetic field, take the time derivative, and you have the rate at which the energy of the electromagnetic field changes. So this is an equation for global conservation of energy. Poynting's theorem gives you an equation for local conservation of energy, gives you a way to follow where the energy is flowing. I'm not going to get into the flow of energy today in today's talk. It's an interesting topic, but we're focused on the energy density and not the energy flux density, not the flow of energy today. Okay. If we use this energy density, let me just mention I have this figure in the upper right, which is the same picture as before. So if this is the way that energy is distributed in the field, then for that sphere of uniform charge, the energy density is at a maximum at the surface of the sphere and fades as you get far away from the sphere, but doesn't go to zero anywhere outside the sphere. Okay, good. So the sort of less advanced way to get at this equation for conservation of energy is through Poynting's theorem, where you can derive this equation from Maxwell's equations in the Lorentz force law on the previous slide. Interestingly, let me just briefly mention that historically, I think things went the other way around. So I was reading Bruce Hunt's book, The Maxwellians, and talking about how Heaviside arrived at the modern formulation of Maxwell's equations with divergences and curls. And apparently it was by studying the conservation of energy. So we got these equations for conservation of energy first, and then got the modern formulation of Maxwell's equations. But from the modern formulation of Maxwell's equations, it's straightforward to derive this equation for conservation of energy. Okay. You can also get this energy density of the electromagnetic field from the Lagrangian of classical electromagnetism when you derive the symmetric energy momentum tensor for the electromagnetic field. I'm not going to go into the details of how that's done, but the 0,0 component of that symmetric energy momentum tensor is this energy density for the electromagnetic field, this particular energy density for the electromagnetic field. There's an alternative canonical energy momentum tensor for the electromagnetic field, something I talk about in more detail in the paper, but something I'm not going to talk about much today. The canonical energy momentum tensor has a different energy density, gives a different energy density for the electromagnetic field, but the canonical energy momentum tensor is not generally regarded as attractive, in part because it's not symmetric. And the fact that it's not symmetric, sometimes said to mean that angular momentum would not be conserved, although there are ways to retrieve conservation of angular momentum by endowing the electromagnetic field with a density of intrinsic angular momentum. So there are moves you can make, but there does seem to be some complicated issues with angular momentum there. Also in general relativity, you want a symmetric energy momentum tensor to serve as in the Einstein field equations. And so the canonical energy momentum tensor won't work for that purpose. Okay, so if we pause here, we've gone from electrostatics to kind of textbook electrodynamics. I think it's very natural to draw the lesson that potential energy has disappeared. We had this option of potential energy that was viable for classical electrostatics, but doesn't seem to be viable for electromagnetism. If we want conservation of energy, we have to endow the electromagnetic field with energy, and the most natural or the standard way of doing so gives it this energy density E squared over 8 pi plus B squared over 8 pi. So we don't seem to have potential energy anymore. And you might say good riddance. You might say, okay, as we get to more advanced or more fundamental physics, we don't need potential energy anymore. We don't have it, and then it's gone for good. But what I will argue is that it actually comes back, and actually it might not have been, even from this equation, it's not clear that it's been removed. Even if we endow the electromagnetic field with this energy density, matter could still have potential energy. So in particular, it matters how we're interpreting or how we're understanding the integral on the left. Is that giving the rate at which the non-electromagnetic energy of matter changes? That's how this kind of equation is often explained. Or is it giving the rate at which the total energy of matter changes as a result of electromagnetic forces, but where that energy of matter might include an electromagnetic potential energy? If it's the latter, then we can still have electromagnetic potential energy. And I will argue that that is what happens in classical Maxwell-Dirac field theory. So even if we give the electromagnetic field this energy density E squared over 8 pi plus B squared over 8 pi, there still ends up being electromagnetic potential energy that the Dirac field possesses. Okay. Before proceeding to that classical Maxwell-Dirac field theory, let me just mention a different equation for conservation of energy that you might study in classical electromagnetism, a sort of alternative, not the standard equation, maybe a deficient equation, but an equation that holds. So on the left, you have the same rate at which energy is transferred to matter by electromagnetic forces. And then on the right, I've rewritten the total energy of the electromagnetic field in the Coulomb gauge using some integration by parts and using the ways of writing the electric and magnetic field, or the electric field, in terms of vector and scalar potentials. So here you actually have the 1/2 rho phi energy density from before as part of your total energy density. And then instead of E squared over 8 pi plus B squared over 8 pi, you have now this dA dt, the derivative of the time derivative of the vector potential appearing. So you might say, okay, this is just a different way to write the energy of the electromagnetic field, but it doesn't mean anything about where the energy actually is. It's still E squared over 8 pi plus B squared over 8 pi. And I think as a way of rewriting that energy, it's useful. If you wanted to take it further and say, no, this actually tells you where the energy is, you actually have that potential energy density from before, and the energy density for the electromagnetic field, it's there. There is energy in the electromagnetic field, but it's not E squared over 8 pi plus B squared over 8 pi. It's this new energy density for the electromagnetic field, the green term here. So that would be a kind of radical way of interpreting this equation. I think there are some downsides to doing that. On the one hand, driving this equation relies on using the Coulomb gauge. So you have a sort of preferred gauge if you're using this as your way of understanding conservation of energy. Also, this energy density is not part of a standard energy momentum tensor for the electromagnetic field. Maybe there's a way to derive an energy momentum tensor for the electromagnetic field that includes this as its 0,0 component, but I haven't seen it done. And so I'm not sure what that would look like. I've seen this kind of trick used in quantum field theory textbooks to re-express the energy of the electromagnetic field. I haven't seen it in classical electromagnetism books. If anyone is aware of where that's discussed, I'd appreciate references. Okay. The main reason I'm putting this up here is that I'm going to come back to it when we come to question 2. This question of why the electron doesn't repel itself. I'm going to use this expression for the energy of the electromagnetic field. So I mention it here for that purpose, but it's kind of a tangent as far as this question of whether there's potential energy in classical or quantum electrodynamics. Okay, good. So in that series of 4 theories that we're going through, we've gone through electrostatics now and electromagnetism. We are now at Maxwell-Dirac field theory. This theory is not so familiar, not so widely discussed, but I think it's very interesting and important. Classical Maxwell-Dirac field theory plugs into classical electromagnetism a particular model of matter modeled by the Dirac field. The Dirac field is something that you see from here and there, but not always clearly explained as a field. So originally, Dirac put forward the Dirac equation as an equation that's like the Schrodinger equation, an equation governing a quantum wave function. But you can reinterpret the Dirac equation as an equation governing a classical field. And I think it's valuable to do so because you get a picture of classical fields that it has a close connection to quantum electrodynamics. So the way this theory works, you have the electromagnetic field as before, maybe specified by E and B, maybe A and phi. You have then in addition, another field in your ontology, you have the Dirac field. No operator valued field here, just a complex valued Dirac field psi. It has a charge density. The standard expression for the charge density of the Dirac field would be minus E, the charge of the electron, psi dagger psi. So when you're thinking of psi as a quantum wave function, psi dagger psi would be a probability density, but here it's not a wave function, it's a classical field, and minus E psi dagger psi gives you a charge density. And then there's also a current density, minus E psi dagger gamma naught gamma psi, where gamma naught gamma are matrices. Okay, so your ontology has these two fields, the electromagnetic field and the Dirac field. Your laws, you have Maxwell's equations as before, so that part hasn't changed. And then you have the Dirac equation giving the evolution of the Dirac field psi. The Dirac equation including interactions with the electromagnetic field. So that's why it's sometimes called Maxwell-Dirac field theory, because you have Maxwell's equations and the Dirac equation. Those are your laws. Okay, good. So this theory is of interest because when you quantize it, you get full quantum electrodynamics. So this is, you can view this as the kind of classical precursor to quantum electrodynamics. I said before that this is just filling in classical electromagnetism with a particular model of matter. We did delete the Lorentz force law, so you might wonder, am I merely filling things in or what? As I see it in this theory, the Lorentz force law still holds, but it's not fundamental. We don't need it in the basic laws of the theory. So the Lorentz force law gives the density of force exerted by the electromagnetic field on the Dirac field. I see these fields as exerting forces on one another. The Dirac field exerts an equal and opposite force back on the electromagnetic field. Okay, so that's the theory. What does conservation of energy look like in Maxwell-Dirac field theory? Well, in green here, we have the previous energy density of the electromagnetic field. In orange, there's a mass term for the Dirac field. Then there's some more terms for the Dirac field. So there's a bunch of things that involve psi. The green part is the 0, component of the symmetric energy momentum tensor for the electromagnetic field, as discussed earlier. The rest of this is the 0 component of the symmetric energy momentum tensor for the Dirac field. When you look at this energy density for the Dirac field, there's a lot going on. You might wonder, does this include potential energy or not? Well, if you notice on the very far right of this big equation, there's the capital A, there's the vector potential. So it seems like then part of the energy density of the Dirac field depends on what's going on with the electromagnetic field. So it looks like we have a potential energy density there, this E psi dagger gamma naught gamma psi dot A. That can be rewritten using our earlier expression for the current density of the Dirac field as -1/c j dot A. So we have this -1/c j dot A candidate potential energy for the Dirac field. You might say, oh, well, before we were always wondering, was it potential energy or was it interaction energy? Should this be viewed as an interaction energy? I think not. I think it's better to view it as a potential energy, in part because if you view it as a interaction energy, it's shared between the electromagnetic and Dirac fields, then you end up with a gauge-dependent interaction energy and also a gauge-dependent energy of the Dirac field alone. Whereas if you include it as part of the energy of the Dirac field, then the energy of the Dirac field as a whole, the energy density of the Dirac field as a whole is gauge independent. You might even more radically try to interpret it as some other kind of EM field energy if you replace J by EM field quantities using one of Maxwell's equations, but then you get a gauge dependent energy density for the electromagnetic field and a gauge dependent energy density for the Dirac field. So that's not so attractive. So anyway, this is a candidate potential energy density, but you might not like the fact that it's gauge dependent. When you do a gauge transformation on phi, a, and psi, it can change. So another option, which is the long blue bar up top, is to say that all of that is the potential energy density of the Dirac field. That would give you something gauge invariant, but you're bundling more into the potential energy density of the Dirac field. So I'll discuss those two options shortly, how you might decide between them. You might also wonder whether any of this is kinetic energy of the Dirac field. I'm not going to try to settle which of these terms should be interpreted as kinetic energy. It might be just the terms involving the gradient here in the middle, or you might also want to include the J dot A term as part of the kinetic energy. So there are a couple options for what you might take the kinetic energy to be. Depending on which option you take to be the kinetic energy, which one you take to be the potential energy, there might be overlap between potential energy and kinetic energy, which you may or may not be okay with. But I want to put aside questions about what the kinetic energy is here and just focus on potential energy. Okay, so at this point, I think potential energy has reappeared. We seem to have a potential energy density for the Dirac field. I mentioned earlier how that was possible, how even if you assign the electromagnetic field an energy density of E squared over 8 pi plus B squared over 8 pi, there could be potential energy, electromagnetic potential energy in matter. And here we see a concrete example of how that could occur. Okay, good. Should we take the big cluster of stuff to be the potential energy density, or should we take the just -1 over C J dot A to be the potential energy density? Here are a couple cases to help illustrate the difference between these options. So first, for a wave packet moving in free space, ignoring any self field of the electron, but just thinking of the electron moving in an external field, we can adopt different choices of gauge. So maybe we adopt a choice of gauge where A is 0 everywhere, or maybe we adopt a choice of gauge where the vector potential A is pointing to the right everywhere and it's constant. Those are going to yield the same electric and magnetic fields. If we take the gauge invariant option for the potential energy density, then the wave packet has potential energy in either gauge, which is kind of weird. Just because the wave packet's moving to the right, it has potential energy in either gauge, even if A is 0, E is 0, B is 0 everywhere. Whereas if we take the gauge dependent option, then in the first choice where A is 0 everywhere, there is no potential energy. But in the second choice where A is non-zero, then there would be potential energy. So the potential energy is gauge dependent, but at least vanishes when A is 0 everywhere. Okay. We can also ask about the Aharonov-Bohm setup. I don't have time to go into a lot of detail on this, so let me just briefly mention that if you have sort of half the wave packet going above and half going below a solenoid, then each one is moving in a particular vector potential A. The gauge invariant option for the potential energy density would say that if both wave packets are moving towards the detector at the same velocity, they're going to have the same potential energy. Whereas the gauge dependent option would say that the potential energies are different for the two wave packets. Okay, so we went fast through the Aharonov-Bohm thing, but thinking about the wave packet moving in free space, I think gives us good reason to prefer the gauge dependent option for the potential energy density. Potential energy was, I think that's more attractive. It's not a knockdown case, but I think thinking of -1 over C J dot A as the potential energy density is attractive, because then at least the potential energy vanishes for a wave packet moving in empty space when the vector potential vanishes. Okay, good. If we do take this -1 over C J dot A to be the density of potential energy for the Dirac field, we can apply it to a bunch of cases as we'd like. We can ask, what does the potential energy look like here or there? One interesting case to think about is a wave packet representing a spinning electron in the Dirac field. In that case, you're going to get this magnetic field around the electron. You might think, oh, well, there's this B squared over 8 pi energy, so the magnetic field increases the energy of the electron, as opposed to if somehow it weren't spinning or weren't generating a magnetic field. But at least if the electron is rotating with a constant current and the charge distribution is fixed, then we can rewrite the -1/c j dot a contribution to the energy as minus b squared over 4 pi. At least that gives the same total integral over all space. So that shows that when you take not just the b squared over 8 pi energy of the magnetic field, but also the potential energy of the Dirac field, and you put them together, the energy of the electron is lowered by its having this current that sources a magnetic field. Yes, it produces a magnetic field that carries energy, but that current lowers the potential energy of the electron. So overall, the fact that there is this current decreases the total energy over what it would otherwise be. So just one example to get a feel for this potential energy. Okay. When you move to quantum electrodynamics, it's difficult to say what the laws of ontology are. I mentioned earlier that you can use a wave functional to represent the quantum state. So I would view that as at least part of the ontology. And then that wave functional or that quantum state will evolve by a Schrodinger equation. In that Schrodinger equation, you have a Hamiltonian operator. The Hamiltonian operator looks just like your energy before that you had in the classical Maxwell-Dirac field theory, but now there are a bunch of hats on it. And so we have an operator instead of just a energy. And in that Hamiltonian operator, the potential energy density from before appears as an operator. And that gives rise to a certain coupling between the Dirac and electromagnetic fields. And so when, for example, you calculate the Feynman rules for quantum electrodynamics, this potential energy term matters, and the potential energy term features in calculating the vertex for interactions between electrons, positrons, and photons. Okay, good. Okay, so brief summary on question 1 before going to question 2. In electrostatics, we had the option of either using potential energy or field energy to ensure conservation of energy. In classical electrodynamics, we had to include at least some kind of field energy, but we showed that even if we include the standard field energy, it's still possible that matter possesses potential energy, electromagnetic potential energy. If the matter is a classical Dirac field, and we take the field symmetric energy momentum tensor to give its energy momentum, to give its energy density, then matter does end up possessing potential energy. And then when you move from classical Maxwell-Dirac to quantum electrodynamics, that potential energy is there as an operator in the Hamiltonian. So following this series of 4 theories, the lesson seems to be that potential energies are part of fundamental physics, at least at the level of quantum electrodynamics. Okay, so that's the close on question 1, but we still have question 2. Why doesn't the electron repel itself? I have a few things to say about self-interaction here, since this is a question of self-interaction. If you have point charges in classical electrodynamics, you face a number of problems of self-interaction. In particular, the electric field produced by the particle itself is not well defined at the location of that particle. It gets stronger and stronger as you get closer to the particle, becoming infinite in strength as you approach it. And depending on which direction you come in from, the electric field would be pointing in a different direction. So you don't have a well-defined self-force. There's one problem. You might just say, well, the point particles don't interact with their own electromagnetic fields. But if you say that, you seem to lose radiation reaction, the fact that bodies are harder to accelerate when they're charged because you need to produce the electromagnetic waves. So that doesn't seem to work. And then you also have problems with self-energy for point charges. So when you calculate the e² over 8 pi energy for a point charge, you integrate that over all space, it's going to be an infinite amount of energy because the electric field gets so strong as you get close to the charge itself. So you have these problems of infinite self-energy. So a bunch of problems for point charges. There are ways to address them. There are ideas about how to make point charges work. I'm not saying point charges aren't viable, but there are problems that must be overcome. If instead you're working with classical electrodynamics with spread out charges, with charge distributions, you don't face the same problems. You can include self-force, it's never infinitely strong. You can make sense of radiation reaction by looking at how those emitted electromagnetic waves move through the body itself and the forces they exert on their way out. So you can account for radiation reaction that way. And self-energy will be finite, not infinite. The electromagnetic field never gets infinite in strength for a spread out charge, as shown with this charged cloud on the left. You do have a problem of self-interaction for extended charge bodies, which is self-repulsion. If you model the electron as this spread out charge distribution, as this cloud of charge, then you'd expect the different parts of the cloud to repel one another. And that's not something that we actually see. So, if you're using extended charge bodies to model big things in macroscopic electromagnetism, then self-repulsion is going to be there, but it's fine. The self-repulsion is real, it's physical. But when you're trying to use an extended model of the electron, then self-repulsion is problematic. Electrons don't really repel themselves. There's different ways to see that electrons don't really repel themselves. One way is to look in quantum chemistry. So in quantum chemistry, in the ways that people approximate the energies of atoms and molecules using Hartree-Fock method or density functional theory or something like that, they explicitly have to drop self-interaction terms, Coulomb self-interaction terms, self-repulsion terms. Okay, good.
Just a general note, Chip, that we have about 5 minutes. You can go a little bit longer, but it will just mean cutting a little bit into discussion time.
Good. Yeah, I was going to mention, I'm running slightly over, but I think I can keep it to about 5 minutes past the hour. I'll try. Okay. So good. So I was saying there is this problem of self-repulsion for a spread out charge distribution. And in particular, that seems like it's going to be present in Maxwell-Dirac field theory. So in Maxwell-Dirac field theory, you can model the electron as this charged cloud. It's this wave packet, this spread out distribution of charge. That charge will be flowing. You can ask where the charge is going. It's moving around generally. You can see where it's moving around. So here's a picture of like a Z spin up electron and what its charge is doing. Its charge is flowing and the current is shown with these little arrows. So the charge distribution is the gray cloud. The current density is the arrows. Okay. So that's kind of what you have at the level of classical field theory if you're using classical Maxwell-Dirac field theory to model the electron. But it seems like you're going to get self-repulsion then. What exactly is a model of a single electron in Maxwell-Dirac field theory? Well, you can decompose a state of the Dirac field into positive frequency modes and negative frequency modes. I'm not going to explain these in great detail, but the positive frequency modes are usually associated with electrons, the negative frequency modes with positrons. So you have these electron modes and positron modes. I think that a state representing just one single electron should be composed of the electron modes, the positive frequency modes, and it should have total charge minus E. So it's that kind of wave packet, a wave packet made of positive frequency modes with total charge minus E. Recall before that we had this expression for the charge density of the Dirac field as minus E psi dagger psi. That looks good for electrons. It's a negative charge density. Doesn't really make as much sense for positrons. Positrons should be positive charge, but if you use net minus E psi dagger psi for the negative frequency modes, you would get negative charge. So I actually think that this is not the best way to formulate a classical theory of interacting electromagnetic and Dirac fields. I think we should revise that charge density to endow the negative frequency modes with positive charge, but that's a bit of an aside here. We're focusing on the positive frequency modes here. Okay. So there's a problem in Maxwell-Dirac field theory, which is, okay, fine, you can model a single electron like that, but how do you model two electrons in classical Maxwell-Dirac field theory? You might say, okay, well, just use a bunch of positive frequency modes, but have the total charge be minus 2E instead of minus E. Just have more charge, more stuff. The problem is when you do that, there's no real way to distinguish the two electrons. There's just a big cloud of charge. So for example, there might be this big spherically symmetric cloud of charge. You might wonder, well, what's the contribution from one electron and what's the contribution from the other electron? You could decompose it into two clouds that look just like that, but they're half as faint and they're on top of each other. Or maybe you want to decompose it into an electron in the top half and an electron in the bottom half. Different ways to do it, but just telling me the state of the Dirac field as a whole, that it has this total charge minus 2e and telling me what the state of the Dirac field is doesn't seem to tell me what the contribution is from one electron or another. And because I don't have a way to decompose this into one electron's charge distribution and another electron's charge distribution, there doesn't seem to be any way to remove self-repulsion in Maxwell-Dirac field theory. There doesn't seem to be a way to include repulsion between electrons, but exclude repulsion within an electron's charge distribution. Okay, so that's kind of the picture of what's going on, the picture of the problem. Mathematically, the problem comes up, well, one way to put the problem is to use that expression for the energy of the Maxwell-Dirac, the total energy in Maxwell-Dirac field theory that we had earlier, what I described as the alternative expression for the energy in electromagnetism. So there's then a Coulomb term here, the 1/2 rho over the distance between the 2 points. So this is the term that would include the energy of self-repulsion, but also the energy of repulsion between different electrons. For a 2-electron state, there doesn't seem to be any clean way to separate out the energy of self-repulsion versus the energy of repulsion between the 2 electrons. This Coulomb term is going to include both contributions to the total energy. Okay. When we move to quantum electrodynamics, you now have a Hamiltonian operator. In the Hamiltonian operator, we now switch from psi to operators for the fields. For the Dirac field, we switch from A to an operator for the electromagnetic field. What I think we also have to do, when we're being careful about the Hamiltonian quantum electrodynamics, is to include these dots for normal ordering. Specifying the Hamiltonian is specifying the laws of the theory, because specifying the Hamiltonian is specifying how the Schrodinger equation is going to work. So for me, at least, the way I understand quantum electrodynamics, this is ground level. So we're asking, what is the Hamiltonian of quantum electrodynamics? What should we posit? What's going to work well? And I think what works well is doing this normal ordering. So I think we should normal order each term. In particular, we should normal order the Coulomb term. In some textbooks, the normal ordering doesn't seem to be mentioned explicitly. In other textbooks, I think they get the normal ordering wrong. They don't normal order the whole thing. But if you do normal order the whole thing, you're able to have Coulomb interactions between distinct electrons, but not have Coulomb interaction of an electron with itself. So briefly, we're going fast because we're low on time here. But briefly, when you expand out the Coulomb term in terms of the positive frequency and negative frequency parts, when you expand it in terms of the electron modes and the positron modes, you get a number of different contributions, but there's one contribution, there's one piece of it that is purely about the electron modes. So let's focus on that, the part that's purely about interaction between electrons. If the whole Coulomb term is normal ordered, then that's going to feature 2 electron creation operators first, then 2 electron annihilation operators. So if it acts on a single electron state, it's not going to do anything. It's going to drop. If it acts on a 2 electron state, then it can give rise to interesting interactions. So you are able to then avoid Coulomb self interaction, avoid the self repulsion, yet still retain Coulomb interactions between distinct electrons. Okay, so now we can close. Is potential energy part of fundamental physics? I think yes. We can identify in classical Maxwell-Dirac theory a potential energy density, and it is retained in quantum electrodynamics. Why doesn't the electron repel itself? Well, in classical field theory it would, but in quantum field theory, it's the normal ordering of the operators that eliminates self-repulsion. Okay, thank you.
Thanks, Chip. That was wonderful. So we're only a couple of minutes past the hour, so let's take a 5-minute break, and then we'll reconvene. My clock right now says 2:05, so let's reconvene at 2:10.